Hello everyone, my name is Ziniu, a PhD student from UCLA. Today I'm going to share our recent work, Generative Pre-training of Graph Neural Networks. This is a joint work with Dr. Yuxiao, Kuansan Wang from Microsoft Research Raymond, and Professor Kai-Wei Chang and Yizhou from UCLA. The success of machine learning is largely relied on data. However, high-quality labeled data is often expensive to obtain or scarce for training large models. On the contrary, unlabeled data is much easier to access in large amounts, which can be 1,000 times more than labeled data. For example, when doing anomaly detection on graph, the malicious account should be annotated by experts, while the size of the whole unlabeled network can be billion scale. A standard paradigm for learning from unlabeled data is unsupervised pre-training. Its goal is to allow a machine learning model to initialize its parameters learned from pre-training tasks with abundant unlabeled data. As there exists commonality between the pre-training and the downstream tasks, the pre-trained knowledge can help the model generalize well even with few labeled data. Pre-training has shown superior in boosting the performance of many applications in natural language processing and computer vision. In NLP domain, the huge success of BERT and its variants have shown that a task to reconstruct the masked input language can help learn very deep transformer model. Also, in CV domain, recent work like SIM-CLR shown to pre-train ResNet with contrastive task, which is detecting whether two image snippets come from the same image. In both domains, the pre-trained deep model can serve as a backbone model and significantly improve the performance of various downstream tasks, such as question answering, image recognition. This success showed that unlabeled data itself contains rich semantic knowledge, and thus a model that can well capture the data distribution is able to benefit for the downstream tasks. Inspired by these developments, we propose to pre-train graph neural networks. The goal of the pre-training is to empower GNNs to capture the intrinsic structure and semantic properties of the graph, so that it can easily generalize to any downstream tasks with few labels. In this work, we specifically focus on large-scale attributed graphs. To learn a general GNN model without labeled data on the graph, the first question is how to design a suitable unsupervised learning task over the graph. We propose to model the graph distribution by directly learning to reconstruct the attributed graph. For example, if we can correctly predict how an Apple's innovation network is evolved, the pre-trained model should capture the structure and semantic knowledge of this graph, which will be beneficial to related downstream tasks. Following the existing discrete generation methods, we autoregressively factorize the probability objective, which means that the nodes in the graph come in an order, and the links are generated by connecting the new arriving nodes to all existing nodes. As we'd like to capture both attribute and structure information, we need to factorize the condition-generated probability for each node into two terms, the attribute and edge generation. However, a naive decomposition will neglect the dependency between each node's attribute with its own edges, which is very essential for GNN model. Therefore, to maintain a dependency between attribute and structure, we incorporate a variable to represent observed edges and decompose the generation into two coupled steps. In the first step, we are given a set of observed edges and generate node attributes. In the second step, we leverage the attribute information to generate remaining edges. We present a concrete example in academic graph here. Suppose we'd like to generate a new paper node whose title is considered as attribute, and authors, venue, cited papers are connected edges. We first mask out some edges and regard the remaining ones as observed edges. The first step is to use the remaining edges to predict this paper's title, which can help capture the dependency between the attribute and neighboring nodes, such as data mining. Next, we use both the observed edge and generated attribute to predict the remaining edges, such as authors, published venue, citations. In this way, we can also capture the dependency between attribute and masked edges, such as KDD. Formally, we can write down the decomposition. With random masking of the edges, the expectation of our generated task is equivalent to the whole graph distribution. For the sake of efficiency, we desire to compute the loss of attribute and edge generation by running GNN only once for each graph. However, when doing edge generation, we will utilize the attribute information as input, which will be an information leakage to the attribute generation task. To avoid such information leakage, we split each node into two sets. The first set is called attribute generation node. We mask the attributes of these nodes and replace them with a dummy token and learn the shared vector to represent it. Another set is called edge generation nodes. For these nodes, we keep the attributes and put them as input. After running GNN over the graph, we will get the two sets of node representation for each node, which will be used for the two generation tasks. To pre-train GNNs on graphs that are too large to fit into the hardware memory, we sample subgraphs for mini-batch training using lattice sampling algorithm. To estimate the edge loss, it is required to go over all nodes of the input graph as denominator. However, we only have access to the sample nodes in the subgraph for estimating this node loss, making the self-supervision only focus on local signals. To alleviate this issue, we propose the adaptive queue, which stores node representation in previously sampled subgraphs as negative samples, which can enlarge the negative sample size. To evaluate the performance of GPT-GNN, we conduct experiments on two large-scale heterogeneous graphs. The first one is Microsoft Academic Graph, which contains more than 200 million nodes and 2.3 billion pages. The other is Amazon recommendation datasets. Here, we focus on the discussion of open academic graph datasets. The fine-tuning task is inferring the topic and value of each paper and author name disambiguation. We mainly utilize heterogeneous graph transformer as our base model. To mimic real-world domain transfer setting, we choose nodes of some specific domains for pre-training and conduct downstream evaluation to a different domain. Specifically, in field transfer, we use all the papers except CS for pre-training and use CS papers for fine-tuning. In time transfer, we use CS paper before 2014 for pre-training and CS papers after 2014 for fine-tuning. We also consider combining the two transfer settings together, which becomes the most challenging setting. Overall, our proposed GPT-GNN consistently enhances the downstream task performance and outperforms other baselines on the different settings, and it achieves performance gain of 9.1%. The two generation tasks are all helpful, and the combined version is the best pre-training objective. We also evaluate the promise of our proposed pre-training method using different percentage of label data. As is shown, GPT-GNN consistently improved the downstream task performance. In addition, we can see that with pre-training, the performance with only 20% of label data is higher than direct supervised learning with 100% data. This shows the effectiveness of pre-training, especially when the label is scarce. We also show the loss curve with and without pre-training. With pre-training, the model can achieve higher generalization performance and more robust to overfitting. Also, we show the generated title in our pre-training task. It seems that the model can indeed capture the overall semantic of each paper, only utilize their neighborhood. We also show that GPT-GNN can consistently improve the performance for various GNN models, but a more expressive model as SGT can receive higher performance gain. Finally, we show that GPT-GNN can be utilized for homogeneous graph too, and get the highest performance gain. The code and dataset are available here. Thanks for listening.